Hello class, this set of videos is going to discuss IR spectroscopy. And IR, it refers to infrared. Remember in the electromagnetic spectrum, which that word is just a fancy way of saying light, that we have visible light, infrared light, UV light. Well, we're using infrared light to study molecules. And what's interesting about light is that when you use light to study matter, that's called spectroscopy. So what we have here, you could take this little electromagnetic radiation right there and just replace it with light. So spectroscopy is the study of the interaction of light with matter. And what we're trying to do with IR spectroscopy is to determine and understand the structure of molecules. That's what organic chemists need to know, is when they make molecules, what do they look like? What are their structures? Erase that there. So we know that there's many different types of electromagnetic radiation, and that's based off of their wavelength. If you have really long wavelengths of light, those are typically radio waves. And if you have really tiny, tiny, tiny wavelengths, then you have gamma rays. And infrared spectroscopy uses IR radiation. So here's that spectrum there to give you a visual of what that looks like. You have gamma rays on the left, all the way on the right, we have radio waves. And then we have this little sliver right here called visible light. And that's what our eyes can detect. But that's just a small sliver in the spectrum. There's so much more. And so this chapter is going to focus on infrared, how infrared interacts with molecules. Now, we've all been to a restaurant where you have your food waiting under a heat lamp. That's infrared. Have you ever seen the movies Predator with Arnold Schwarzenegger? The Predator uses infrared light to see. But we're not in the movies and we're not in the food industry. We are chemists, and we can use infrared to study molecules. In order to fully understand and appreciate IR spectroscopy, we need to remind ourselves of what light is, how it behaves, and some of the rules or the principles that we've learned about light. And the first thing that we've learned from general chemistry is that light can behave like a wave and it can behave like a particle. And depending on how you're looking at light determines which equations you use to describe light. So I want to go through that really kind of do a crash course of that with you because it's really important. So if light behaves as a wave, we can describe light with this formula. C equals nu times lambda. Recall that C right there stands for the speed of light. Lambda is the wavelength. And nu is the frequency. And what this shows us here is that that the frequency and the wavelength have an inverse relationship with one another. And what I mean by that is if we have a frequency and we increase the frequency of the light, what's going to happen to the size of the wave or the wavelength? Well, the wavelength is going to decrease. When frequency goes up, wavelength goes down. So let's look at the slide here. So look at this. Radio waves have a big wavelength, small frequency. But as we increase the frequency, following this red arrow, what happens to the size of the waves? They get smaller. And so we could say the opposite as well. If the frequency goes down, what happens to the wavelength? It's going to increase. Okay? So there's that inverse relationship. Now, if we look at light as a particle, we have to use this equation right here. The energy of a photon. And the photon is the particle that is describing light. So light now behaves as a photon. And the energy of that photon is going to be related to Planck's constant times the frequency. Recall that Planck's constant has a value of 6.626 times 10 to the negative 34 joules times seconds. And that's going to tell us the energy there. Now, energy is going to be directly proportional to frequency. So we can say energy of a photon is going to be directly proportional to its frequency. Okay? So that simply means that if the frequency of the photon of light increases, what's going to happen to the energy of that photon? The energy is going to increase. So if the frequency decreases, then the energy will also decrease. And we can see that right here. Radio waves are all around us, but they have such large wavelengths, which means they have a very low frequency. And a very low frequency means very low energy. So these wavelengths right here are not dangerous. They won't cause us cancer and get us sick. But UV light has a higher frequency, so it's higher in energy. So you get sunburns. If you go to the dentist and get x-rays, much higher frequency, higher in energy, more dangerous. So it is very important to understand that relationship between energy and frequency. Okay. Okay, that's what I want to say about that. That's just a crash course, going through that fast. So here's the IR radiation. And IR radiation has a range of 800 nanometers all the way to 10 to the 6 nanometers. Okay, so it's in that range right there. What's cool about it, one cool thing is that we can't see it, but we can feel it because it gives off some heat. So this is the instrument it's a model of an IR spectrometer that chemists use to help determine the structure of molecules. And what you do is you have this little arm right here that is raised up. And then on this little plate right here, you put your sample. And then you take the arm and put it back over your sample. And then you click a few buttons on the computer to set the parameters and everything. And it's going to shoot infrared light at your sample. and then a detector is going to detect how the light interacts with the molecules or your compound that you placed on the IR. So so the general principle of IR spectroscopy is as follows. What's going to happen is, let's put it here, let's draw here. So what happens is what I'm going to draw right here is that little platform where you take your sample. So I'm going to put a little sample right there. Okay. So this little diagram right here is I'm representing that little disc right there. Okay, that little disc. Okay. And so what happens is the idea here is we're going to zap our sample, okay, with IR radiation. And then that light is going to travel through our sample and hit our detector. Okay. And then that detector then sends out the information to our computer. So what's typically happens is that we know the frequency of IR radiation that we are zapping our sample with. Okay? So I'm drawing this as a thick arrow because we are going to zap it with a lot of light. And we know that frequency. We know it. And what happens is that that light is going to hit our sample, travel through the sample, and then we are going to get less IR radiation hitting the detector. And so what's happening is that we have more light up here, less light down here. So where did that light go? Where did that energy go? Well, it was absorbed by our sample. And based off of that absorption, the detector and the computer works together to give us some very useful information to help us understand the structure of the molecule. Okay, and so what we're going to delve into is the theory behind this, and then we'll talk about principles that will help us use IR to determine the structure of molecules. In order to understand more of the theory, we're going to simplify it and look at molecules like this. So if I have a carbon atom, I'm going to look at it like a ball. And then that carbon atom is going to be connected to another carbon atom that also looks like a ball. And we know from general chemistry in Orgo 1 that carbon-carbon bonds are represented by a line, which that line represents electrons. Right? And so that right there is going to be our sigma bond. But for IR spectroscopy, now let's envision that that bond is a spring. A spring that connects the two atoms. Okay? Now, many of you have played with a slinky or a spring, and you know you can stretch a spring, right? Same thing with atoms. They are not connected by a metal bar. That's very, very stiff. Atoms are connected more by springs, and so they can move and they're flexible. Okay? And so we have different, how can I explain this? In quantum mechanics, you have what's called vibrational motion. Okay? And so if you envision this spring, there's different motions. So you could take the atoms and stretch them. You could take the two atoms and compress them. You could take the springs and twist them. So all of these motions, we term them vibrational motions. And there's two basic terms. One is called a stretch, and one is called a bend motion. There's two types that we want to look at. Okay, and formaldehyde, we're going to look at a molecule called formaldehyde, and we're going to show you, or I'm going to show you, the different stretches and the bending modes that formaldehyde can undergo. So up here, up top here, is formaldehyde. Okay. Now we could see that we could stretch the carbon-oxygen bond like this, and then we can also compress it. So that is an example of a stretch of the carbon-oxygen double bond. In the stretch category, there's a subclass called symmetric stretches and asymmetric stretches. And you can see in this little box here that we have a symmetric, going from this version to this version, we have had a symmetrical stretch. Okay. But then from this one in the middle to the one on the right, we have a symmetrical compression, which we still call it a stretch. Okay. So we have these stretches here, and that when that happens symmetrically, those stretches occur at the same time. Okay. And in the same direction. The asymmetrical stretch you can see in this diagram. One bond is compressed, whereas the other bond is stretched out. And so you get something that looks like this in the middle, and then the other version on the right. So those are stretches. Now we can also do something called a bend, where you can see that these two hydrogens, not only can we stretch and compress them, but we can bend them closer to one another, like this, or we can bend them out further from one another, shown right here. Okay, and that there's another two subclasses here of these bends here. We have in plane versus out of plane. Okay. And then you can see here some examples of out of plane bending. So all of these right here are called vibrations. And we have different vibrational modes. So here's a vibrational mode, and so forth. You can count all these up, and they're different vibrational modes. Okay. Now, when we treat and look at molecules, look at them as if they have springs on them, quantum mechanics is going to tell us that each one of these vibrational modes is quantized. Energy is quantized. What does that mean? Okay. And I'm going to simplify this here. If we have on our y-axis energy here, we could have a vibrational mode that looks like this. Here's formaldehyde. Okay. But then formaldehyde could have a different vibrational mode, higher in energy, that looks like this. Do you see how I stretched? That needs to stay about the same size. See how I've just stretched the carbon-oxygen bond? Well, that's a different vibrational mode. Okay. And so that energy is quantized. This vibrational mode is at this energy level, and we could put numbers on this y-axis that quantifies the energy of that state. And then this is quantized at this energy state, which then would have a number associated with it. The numbers aren't very important to understand this concept here at this point, okay? But we have two different vibrational modes, and those energies are quantized. They have a specific energy. So for each normal mode, therefore, only certain energy levels are allowed. So only photons of certain energies can be absorbed. So what that's talking about is that if we want to go from this vibrational mode to this vibrational mode and energy is quantized, we have to zap this molecule or this vibrational mode with IR radiation. And this IR radiation, its energy has to match this energy gap perfectly. So if we zap this mode with this amount of energy with an infrared photon, then we can promote this molecule to do that stretch. And now the molecule is going to be in this energy state. Okay? But what if I zapped the molecule with this much IR radiation, and the energy of that IR radiation is only this much? Well, if I zap this molecule with that much energy of IR radiation, nothing will happen because energy is quantized. The only way that you can get this molecule to enter this vibrational mode and look like that is if you zap it with that amount of energy, which has to equal that energy gap. That's what quantized energy is talking about.